Good evening, class. Good evening, class. Good evening, class. Bright and raw.
Good evening, sir.
Yeah, how are you?
I'm fine, please, Sonia.
Yeah, I'm also doing well. Yeah. So I want to begin today's class. Okay, and as you're aware, I sent the lesson note to you. That was yesterday, and there are many other related videos. Okay, in relation to what we are doing today on my YouTube page. Okay, so you can just check for those related videos as we go along and watch them before coming to class so that, and also watch other related videos to the topic, okay, to make the class more exciting when you come. Okay, so to begin today, we're looking at and before I start, the material I sent to you is a summary note for this week as well as next week. Okay, where we'll be focusing this week. We are wrapping up on solutions to linear system. Okay, and we'll begin with numerical solutions to differential equations. Okay, in the next class, and we'll be looking at the number of techniques till that's next week. We'll wrap up on these topics by next week. Okay, so you take note of that. I intentionally sent everything to you so that sometimes the pressure. So you might end up skipping a lesson note. That's why I've sent everything to you. So take note of it and revise accordingly. Good. So like we've said, we're wrapping up on solutions to linear systems today. Okay. And later, the next class, we will start with numerical solutions to differential functions. Good. Our topic for today is Jacobi and Gauss Seidal techniques. Okay. In the past week, we've been looking at solutions to linear systems, and we started with the Gaussian elimination technique. Okay. And as our objective in class, we said we had to reduce the system into an upper triangular matrix. Okay. And then we use the backward substitution to solve. And the main intention of doing that is to get the process, okay, a step-by-step process or algorithm, which we can employ to write a computer program which can solve any given system of linear equations for us. Okay, and we realized that the Gaussian technique would offer some limitations, okay, with regards to the process, the step-by-step process, okay, because there are different ways of solving the same problem. Hence, the need for us to go to pivoting technique, which was more formalized with an equation. Okay, so based on the equation, we could select our pivot, and then based on the equation, we obtain the multipliers which are used in reduction. Okay, then after going through the pivoting technique, we realized there was a little challenge with the technique as well. Okay, and the challenge was with having a pivot which was equal to 0. Okay, now once we get a pivot that was 0, then it means that our multipliers were going to be what? Undefined. Okay, so we had to resolve that using what a scaled pivoting technique, which allows us to optimize, okay, the LIs, okay, estimated using the absolute of AIs, okay, over the maximum value of the absolute of the AIJs. And then once we obtain the maximum LI value, okay, or the optimum value, we can base on that optimum value to do what? To select our pivot, our pivoting row, okay, and for that matter, the pivot which will be used in subsequent analysis. And we said that that addresses the challenges of the pivoting technique, okay, and then based on that technique, we could easily write a program, okay, which can be used to solve any system of linear equation. And follow up on that, we had an assignment, I think assignment 5, okay, which is intended for you to write a computer program to solve any given dimension of linear systems. Good. So today we are continuing, and I think we introduced ourselves to the Jacobi and the Gauss-Seidal technique last week. Okay, we said the process was quite simple. We just had to do a change of subjects for x1, x2, x3, and then we use an initial point, okay, for the iteration. Now, before we can proceed, like we said, okay, the Jacobi method makes two assumptions, okay. The first assumption is that the given system of equations should have a unique solution. Okay, should have a unique solution, meaning the solution should exist. Okay. Of course, we know that a given system of linear equation may have a unique solution, may have infinitely many solutions, or could have no solution at all. Okay, so the first assumption is that the solution of the system must exist for us to make use of what? The Jacobi technique. And then again, that the coefficient of the matrix A, of the coefficient matrix, okay, has no zero entries on its main diagonal. So the element on the diagonal of your coefficient matrix, okay, should not be equal to what? 0. There should be no 0. All the values A11, A22, A33, A44 should be non-zero. Okay. These are the two assumptions to the system. Very good. Now the question is then, how can we ensure that these conditions are satisfied, that it has a solution and that there are no or nonce the elements on the diagonal, on the main diagonal, are non-zero. Okay, good. An easy way of identifying this is using the straight diagonal dominance, okay, proof or approach. Okay, now we say that a matrix is straightly diagonally dominant, okay, when elements on the leading diagonal, the absolute of the elements on the leading diagonal of each row exceeds or is equal to the sum of the absolute of the other elements in the same row. So for example, if we have a matrix, okay, we got a matrix, let me put that down. Okay, so for example, we have a matrix 3 minus 2 1 1 negative 3, okay, 2, and then we have what? Negative 1, negative 1, 2, and what? And 4. Okay, so this is the coefficient matrix A for the system. Okay, now what we are saying is, if you pick row by row, okay, for this formula we are having here, the formula is not showing well, though it's very correct on my slide. So the formula should be absolute of AII, okay, should be greater or equal to what? Or equal to summation of J not equal to I, okay. Then we have what? Absolute of what? AIJ. So this is what the straight diagonal formula is for all I and what? And J. So what we are saying is if I is equals to 1, okay, if I is 1, I equals to 1, then the formula will become what? Absolute of what? A11, okay, should exceed or be equal to the summation of what? J, which is not equal to what? 1, okay, to, okay, we have 3 values of the column, okay, 3 columns, so 1, 2, 3, so to 3, okay, for the absolute of what? A, okay, A1, J. Okay, so if that is the case, then A11 is what? Or better still, let me expand this right form, okay? The expansion will just be what? J is not equal to 1, which means that J can be 2 and J can be 3, okay? So the summation will just be absolute of what? A2, A1, A1, 2, okay, plus A, okay, 1, 3. Okay. Yeah, so this is expansion. So it means that the absolute of the value on the leading diagonal or the pivot should be equal to the sum of the absolute of the other elements in the same row. So A11 here will be absolute of 3, okay, should be greater than or equal to absolute of A12, absolute of A12 here, which is what? -2, plus the absolute of what? A13, which is what? +1. Okay, so this will give us 3, should be greater than or equal to what? Absolute of -2 is 2, plus absolute of 1 is 1, okay? And this is what? 3 is greater than or equal to what? 3, okay? Which satisfies the condition. Okay, so this is just for I equals to 1. Now, if okay, so when I equals to J, then the formula becomes absolute of what? When n equals to 2, the formula becomes absolute of A22 should be greater than or equal to absolute of what? This time, your I is what? 2, so your J cannot be 2, okay? So we're going to have 2, 1 plus what? Plus absolute of AI. J has the values 1 and 3. It cannot be 2. Okay. So A22, this is A22. Okay, so we have absolute of -3 is greater than or equal to absolute of what? A21. Is it 1? Absolute of 1 plus absolute of A23, this is it, 2. Okay, so absolute of A23 is 2. And then this will give us what? This gives you 3. Once again, it will be 3. Okay, is greater than or equal to what? 3. Okay, so the condition is also what? Satisfied when I is equals to 2. Then for row 3, where I is equals to 3, okay. So in the case where I is 3, the formula becomes A33 should be, now I is 3, so J can only be 1 and 2. So we have A, I, J is 1, and then A, I is 3, J will be 2. So A33 is 4, A31 is -1, and then A32 is what? +2. So when we find that, we should give us what? 4. Okay, that should give us 4. Okay, this should give us 1 plus 2, which equals to 3. So that's 4 is greater than or equal to what? 3, which also what? Satisfies the condition. Okay, so once these conditions are satisfied for all the rows, 1, 2, 3, then we know that this matrix is what? Sddm, strictly diagonally dominant what? Matrix. Okay, so once all the conditions are satisfied, we know that the matrix is a strict diagonally dominant matrix. Now, why do we even have to look at straight diagonal dominant matrix when the main topic is on Jacobi and on Seidal? Now, the properties of Sddm matrix, okay, are such. For Sddm matrix, we are always sure that if a matrix is Sddm, is strictly diagonally dominant, then the matrix is invertible, okay? In other words, it's non-singular, which means that the determinant exists and the inverse will also exist. In other words, the solution will also what? Will also converge, okay? Yes, so which implies that if this matrix is Sddm, then we are 100% sure that the matrix, the solution exists, okay? Once the solution will exist, if we apply the Jacobi and the Gauss-Seidal method, we are sure that the method will surely what? Converge. Because the solution exists, the method will what? Converge to the solution, okay? But if you are not sure that the solution will exist and you are using iterative methods like Jacobi and Gauss-Seidal, okay, you are not certain that this solution really exists. You understand? But when you investigate whether the matrix is Sddm and you find out that it is, then it means that the solution is not singular, which means that the solution will also what? Exists. Hence, you can proceed and what? Apply your Jacobi and the Gauss-Seidal method. And you are very certain the solution will converge regardless of the number of steps you are going to what? The number of iterations you are going to compute. Okay, any question? Any question? For those who just joined, okay, we looked at the concept of strict diagonal dominance. And in short, we are saying that if a matrix is strictly diagonally dominant, or SDDM, okay, then it is a non-singular matrix. In other words, it's invertible and the inverse of the matrix will exist, okay? In simple terms, the solution of the matrix will also exist, which means that applying the Gauss Seidal and the Jacobi method will converge toward a solution, okay? So the method, that investigation assures us, okay, of obtaining a solution when we use an iterative technique. Okay. Let me zoom in a bit. Yeah. So for the Jacobi technique, like I introduced last week, given any system of matrix, what you do first is to, okay, re-express the equation, or to make x1, that's if it's a 3 by 3 system, you make s1 the subject in the first equation, s2 the subject in the second, s3 the subject in the what? In the third equation, okay? Depending on the number of equations at hand. So if it's an n by n matrix, then we expect to have x1 is equals to what? You transfer all the other variables on the left to the right hand side, okay? So we're going to have the solution b minus x2 with its coefficient, s3 with its coefficient, minus dot 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 to the last term, okay? And then you divide through by the coefficient a11 of what? X1. Then you do same for x2, you do same for s3, you do same all the way to xn. So that is the first step, okay, of the Jacobi and the Gauss-Seidal method as well. Okay, let's proceed. Then in the second step, okay, what you do is you make an initial guess. You make an initial guess, or you select an initial what? Guess, P. So usually you'll be given the initial guess P naught, okay, and P naught will consist of what? The initial values of x1, s2, s3 to xn. So if it's a 3 by 3 system, I could give you P naught, okay, which is the initial guess, to be 0, 0, okay, 1. 0, 0, 1 means that x1 is what? X1 is 0, S2 is 0, and then S3 of the system is what? Is 0. These are the initial guess, okay, which will be employed in the first what? Iteration, okay? Good. So what we are saying here is, once we are giving this initial guess, you substitute these values into the right-hand side of the rewritten equations to obtain the first approximation, okay? Yeah, you do the first approximation by substituting the initial guess, okay, into the rewritten equations, which we did in step 1, okay, to obtain the first approximation, which will be what? X1, X2, X3, okay, to Xn, depending on the size of the matrix, or the size of the system, okay? Very good. And then this is just the first iteration, okay? So when we talk about iteration, we are just substituting the point to estimate new values, which will be used for subsequent what? Approximations. Then the next thing you do is, in the same way, the second approximation, x1 new, s2 new, s3 new, to xn new, is computed by substituting the first approximation values into the right-hand side of the rewritten equations. Okay, then once you are done, you repeat these iterations, okay, and form a sequence of approximations SK. Okay, so you'll be running the iteration a number of times till the solution word converges. Okay, and then we'll know when we say a solution has converged, then it means simply that let's say you've completed a 10th iteration. Okay, so you had your 10th iteration, that is P10. Okay, and your solution at that point for the system was, let's say it's a 3x3 system. You obtain 233. Okay, good. Now, if this is indeed the solution of the system, then it means that when you, okay, substitute it back into the right-hand side equations, and then you run the 11th approximation. The 11th approximation, which will be P11, will also be what? 2, 3, 3. Why? Because we all know that a solution of a system satisfies what? The equation of the system. A solution satisfies the equation of what? A system. For example, if you say 2 plus x is equals to 3, 2 plus x is equals to what? Is equals to 3. And I ask you to find the solution of the system, right? Then when you take this to this side, that will give you 1. So x is equals to 1, right? X is equal to 1 is the solution of the system. The solution of the system simply means when I plug 1 into the function here, okay, then it must satisfy what? It must satisfy the system. So 2 plus 1 should be equal to what? 3. So at this point where the solution has converged, if you plug it back into the 3 equations, you still get the same, P11 to be what? 233, which tells us that you have to stop your iteration at what? This point, okay, which is P10, okay? That is where the solution converges. And like I said earlier, in order to be sure that you are going to obtain a solution from this Jacobi or this iterative method, you need to test whether the solution of the system really exists by checking if it is what? Sddm. Okay, let's continue on. Any questions? Any questions? Okay. So we've explained this. Let's move on to the next slide. So we got an example here to try. Okay, and we've been told to apply the Jacobi method to solve the system 5x1 minus x2, 2s2 plus 3x3. Okay, so let's keep this as s3 is equals to that. So like we said, first you have to rewrite the equations, okay? So your first equation is going to be what? You take all the other variables to the other side, okay? So this will be 1 over 5. This is 1 over 5 into bracket the solution, which is that's b minus 1, okay, minus what? We are taking s2, so that will be plus 2x2, okay, and then minus what? 3x3, okay, good. Yeah, so that gives us our x1. So you may choose to expand it in this form. It doesn't make any challenges. any difference. Okay, then we also have S2, you do that the same way. Okay, so either you write it in this form or you write it in this form. It doesn't make any difference, like I said. Then once you have written the equation in this form, that is the first step. Okay, so you want to have an initial guess, which will be provided, okay, in examination. The initial guess will be provided for you. So in this question, we are giving the initial guess as what, which is P naught as what, as 0, 0, 0. So we get our initial guess to be 0, 0, 0. Okay, so if 0, 0, 0, then pair the equation. Okay, let me do this. I want to edit the slide a bit. We'll substitute 0 in here and then 0 in here. Okay, then we'll do the same as well here. X1 is 0, S3 is 0, S4 is 0, and then X5 is also what, 0. Okay, sorry, X1 and X2 are what, both 0, to get your what, X3. Okay, so that is the what you are seeing on the next page, which I showed you earlier. Good. So this is what you have. So this quantity goes to 0. This also goes to 0. Okay, and we are left with what? Minus 1 over 5. Okay, which is what? 0.2 negative. Okay, good. Then similarly, this will also go to 0. This will go to 0. We are left with 2.9. Then we also have this as 0. We have this as 0, which is what? Negative 3.4. 3 over 7, which gives you negative 0.429. Okay, so that will be the very first what? The very first iteration. Okay, very good. So let's take note of this. That's 0.2, 0.22, and then 0.429. Good. Which means that in the next estimation, we are going to use this. This is our P1. Okay, so P1 is what is, first let me clear the screen. So P1 is negative 1 over 5. Okay, that's 2 over 9. And then we have negative 3 over 7. Okay, very good. Now somebody will ask, why am I not using the decimal what values? Okay, yes, I do not want to encourage you to approximate your solution. Okay, because I told you from the beginning of the numerical methods that once you introduce an input error into your algorithm, the process has its own amount of error, and with your error introduced, your input error introduced, they will combine and then enlarge the output what error. Okay, so unless otherwise stated in the question to approximate to maybe about 3 decimal places or 4 decimal places, you want to keep your calculations, okay, in the fraction form, okay, rather than running them in decimals and approximating the values of your xi's. Okay, so we want to do the next iteration, which will be for P2. Okay, good. So I'm going to go back. Yeah, so when we come here, this is your new value of P1. I'm sure you have your calculators by you. Okay, you should have your calculators by you. This topic, you need to run a lot of calculations. I'm just introducing you. You have to do the calculation yourself to understand. Okay, so once I'm done, you are going to continue with this one. Okay, you're going to continue with this till we get the final answer. Okay, so the next step is to substitute S2 is, this is S2, so 2 over 9. So you're going to get negative 1 over 5, okay, plus what? 2 over 5 into bracket what? 2 over 9, which is your x2, okay, minus 3 over 5, minus 3 over 5 times your x3, which is what? Negative 3 over 7. Over 7. So you calculate this and then do same for x2 and what? X3. Once you are done, the values you obtain will be your P2. Okay.